Welcome back to Nutrition 101. This course follows Sizer and Whitney's Nutrition, Concepts and Controversies, 16th edition, but I've made adjustments by skipping and rearranging some of the material and adding my own images and information. This video covers Chapter 5, the lipids, which continues our journey into the 3 macronutrients, having just completed carbohydrates. Fat is the word that's used most often to describe this macronutrient. Lipids represent a larger group of molecules with similar characteristics. The learning objectives for this lesson are to discuss the usefulness of lipids in the body and in food, examine the 3 classes of lipids, explore the basics of fat metabolism, emphasizing digestion, absorption, and storage, and discuss nutrition recommendations for fat. Lipids can be defined as a family of organic compounds that are insoluble in water. That means they're incapable of being dissolved in it. For example, carbohydrates are soluble in water, so if you mix table sugar with water and stir it, the sugar dissolves in the water to form a solution. But if you take the same water and add olive oil to it, the olive oil will not dissolve. It will separate and sit on top even if you stir it. There are 3 major classes of lipids. Those classes include triglycerides, phospholipids, and sterols. We'll dive into each class in the second section of the video. First, we'll look at the functions of lipids as a whole. For this, we're asking, how are lipids useful in the body? Lipids serve as a significant fuel source, which they share with the carbohydrates. In Chapter 4, we learn that glucose is the exclusive fuel source for red blood cells and the preferred fuel source for the brain and central nervous system. While that is undoubtedly critical for survival, fat provides 80 to 90% of the body's energy at rest. Lipids also serve as the chief form of stored energy. Whereas there's limited storage for glycogen in the body, the capacity for fat storage is basically unlimited. That can be helpful in times of famine or disease. However, it can be harmful when considering the consequences of obesity. Beyond serving as an energy source and form of stored energy, lipids provide padding and insulation. In fact, having some fat on the body, especially within the abdominal cavity, is necessary because fat protects internal organs from collisions and cold temperatures. Finally, lipids serve as raw materials for cell membranes and other essential compounds, including vitamin D, sex hormones, and bile. In other words, lipids form their basis, and without an adequate supply of them, the production of each one can suffer. We can see the role of lipids in padding and insulation by looking at a section of skin tissue. The yellow and orange material is adipose tissue, also known as body fat. It serves as a line of defense over the muscle tissue throughout the body and also exists within the abdominal cavity. Adipose tissue consists of individual fat cells called adipocytes, which can store excess fat and release fat when needed. We can also see phospholipids as an example of the body using lipids as raw materials. Phospholipids are a foundational component of cell membranes, which help keep cell contents inside the cell and allow for the selective exchange of nutrients with fluid outside of it. Now that we've seen how lipids are useful in the body, another question we're asking is, how are lipids useful in food? Lipids provide a concentrated energy source at 9 calories per gram. That can be useful to those who are sick and have low appetite and a decreased ability to eat, and for populations like soldiers and hikers who require a lot of energy but have little room to carry food. Lipids also aid in the absorption of the fat-soluble vitamins. That includes vitamins A, D, E, and K. Lipids play a role in satiety, which is the satisfied feeling of being full after eating. That occurs through the stimulation of gastrointestinal hormones. Lastly, lipids add to the sensory quality of foods. Fat adds aroma and flavor to foods and contributes to crispiness and tenderness. Here are some familiar sources of lipids in the diet. Vegetable oils and butter find their way into many foods. Other sources include animal-based foods like steak, salmon, and cheese, and plant-based foods like avocado, peanut butter, almonds, and dark chocolate. Okay, that completes the first learning objective. Discuss the usefulness of lipids in the body and in food. Now we're going to examine the 3 classes of lipids. Once again, the 3 classes of lipids are triglycerides, phospholipids, and sterols, and we'll tackle them in this order. Triglycerides are the primary form of fat in the body and in food. They're composed of 3 fatty acids attached to a glycerol backbone. Every triglyceride has that glycerol backbone and 3 fatty acids. The fatty acids are what we absorb and then use for energy in the body. Glycerol gets absorbed too and can find its way into the energy production pathway for glucose. In this image, all of the fatty acids look the same. Still, many different fatty acids exist in foods, and they differ in chain length and degree of saturation. Moreover, a single triglyceride can consist of different combinations of fatty acids. Later in the lesson, we'll see how the chain length of the fatty acid impacts absorption. For now, we'll focus on the degree of saturation. Saturation refers to the number of double bonds present in a fatty acid. Saturated fatty acids contain 0 double bonds, whereas unsaturated fatty acids contain 1 or more double bonds. The degree of saturation affects the physical properties of food. Specifically, it affects the melting point. Saturated fatty acids are more solid at room temperature. Unsaturated fatty acids are more liquid at room temperature. The degree of saturation also affects the physiological impact of the fat we consume. Here, we see that an excessive intake of saturated fatty acids raises blood cholesterol levels. That's problematic because it damages the blood vessels, triggers an inflammatory response, and contributes to a buildup of plaque implicated in the development of cardiovascular disease. Here's an image of the molecular structure for saturated fatty acids and unsaturated fatty acids. You can see how the saturated fatty acid has 0 double bonds between the carbon molecules. Then there are monounsaturated fatty acids, which contain a single double bond, and polyunsaturated fatty acids, which include more than 1 double bond. This slight difference impacts the melting point, so saturated fat is solid at room temperature and unsaturated fat is liquid. Examples of saturated fat include butter and the fat visible in beef, vegetable oils, fish oil, nuts, seeds, and avocados are examples of unsaturated fat. The fat in nuts, seeds, and avocados appears solid at room temperature, but only because fiber holds it together. Most saturated fat is of animal origin, and most unsaturated fat is of plant origin. A common exception is coconut oil, which is plant-based, but is composed primarily of saturated fat and is therefore solid at room temperature. Next up, we have phospholipids. Phospholipids are composed of 2 fatty acids, a phosphate group, and a glycerol backbone. The phosphate group makes phospholipids soluble in fat and water. Here's what phospholipids look like. The 2 fatty acids create the hydrophobic tail. That's the side that's soluble in fat. The phosphate group creates the hydrophilic head. That's the side that's soluble in water. This ability to be soluble in both makes phospholipids unique. It gives them their function, which is to serve as emulsifiers and the key structural component of cell membranes. Emulsifiers reduce the tension between water and fat, allowing them to mix. Emulsification is critical to food manufacturing and fat digestion. For food manufacturing, phospholipids allow for the creation of everyday products like mayonnaise. The primary ingredients in mayonnaise include oil, vinegar, and water. Unfortunately, when those are put in the same container, the oil separates from the vinegar and water. However, if you add egg yolks, they mix together. Eggs are rich in phospholipids and allow for the oil to get dispersed in the water-soluble components. Another example is margarine. Margarine is a butter substitute people use to reduce calorie intake, reduce saturated fat intake, if they're avoiding animal-based foods, or if they prefer the taste of it. It's made with vegetable oil and water. To get these to mix, phospholipids are added. That's usually in the form of soy lecithin, which is extracted from soybeans. Then, when it comes to the human body, emulsification plays a significant role in fat digestion. Fat enters the small intestine as a fat globule that cannot be dispersed in digestive juices, and therefore cannot interact with enzymes to be broken down into its individual and much smaller components. However, the bile produced by the liver and released from the gallbladder is rich in phospholipids, and it emulsifies the fat to create emulsified fat droplets. Those droplets are then dispersed in the digestive juices and able to interact with the enzymes secreted by the pancreas. The third and final class of lipids is sterols, which we will discuss the least in this lesson. Sterols are rings of carbon with side chains of carbon, hydrogen, and oxygen. Thus, there are no fatty acids or a glycerol backbone. Sterols serve as raw materials for cholesterol, which is used to make bile and cell membranes. Sterols also serve as raw materials for vitamin D and sex hormones like testosterone and estrogen. Alright, that concludes the second learning objective. Now that we've examined the three classes of lipids, we'll explore the basics of fat metabolism, emphasizing digestion, absorption, and storage. With fat digestion, the goal is to break triglycerides down into free fatty acids. After all, we want to absorb the fatty acids so the body can use them for energy. When we eat fat, little digestion occurs in the mouth and stomach, and fat globules separate from the watery stomach contents. Most of the digestion occurs in the small intestine. The gallbladder releases bile and it emulsifies the fat globules, and the pancreas releases enzymes that split fatty acids from their glycerol backbone. Once digestive enzymes split most of the fatty acids from their glycerol backbone, they get absorbed alongside the other lipids. All lipids are absorbed in the small intestine with assistance from bile. Bile shuttles the lipids into the intestinal cells. Chain length determines where fatty acids end up. Short and medium chain fatty acids are absorbed directly into the blood. Long chain fatty acids are packaged as chylomicrons and released into the lymph. The body forms chylomicrons so that lipids can eventually travel in the blood without separating and being unable to interact with the cells of tissues. Notably, long-chain fatty acids make up most of the fatty acids in food. Here's an illustration of lipid digestion and absorption of long-chain fatty acids in the small intestine. The fat enters the small intestine as fat globules separated from the watery digestive juices. Then bile turns them into emulsified fat droplets, allowing them to mix and be acted on by pancreatic enzymes. Bile shuttles long-chain fatty acids into the intestinal cell, where they're turned back into triglycerides and packaged as chylomicrons. The intestinal cells release chylomicrons into a lymph vessel, where they travel all the way up near the heart before they get dropped off into a major blood vessel. Chylomicrons are a form of lipoprotein, which combines lipids and protein and allows lipids to travel in the blood to the cells of tissues. In addition to triglycerides and protein, chylomicrons contain cholesterol and phospholipids. Finally, we have fat storage. Fat is stored as triglycerides in adipose tissue, which is a very efficient process with nearly unlimited capacity. Fat storage occurs in the setting of excessive energy intake, and since there's an unlimited capacity for it, as long as excessive energy availability persists, a person will continue to see increases in adipose tissue. This process, of course, can be reversed by creating an energy deficit. When the body needs energy, adipocytes break down stored triglycerides. The adipocytes release free fatty acids into the blood for cells to use. As Sizer and Whitney put it on page 151, the way to use more of the energy stored as body fat, then, is to create a demand for it in the tissues by reducing the intake of food energy, by increasing the body's expenditure of energy, or both. In other words, if you want to reduce the amount of adipose tissue in your body, you need to create a demand for energy by eating fewer calories, burning more calories through exercise, or doing a combination of the two. Okay, that completes the third learning objective. Explore the basics of fat metabolism, emphasizing digestion, absorption, and storage. Let's finish Chapter 5 by discussing nutrition recommendations for fat. First up, we have recommendations for daily fat intake. The AMDR for fat is 20 to 35% of total calories. To illustrate this recommendation, we can pretend we have Miss Jackson who requires 1,800 calories per day. If we take 20% of 1,800 and 35% of 1,800 and then divide by 9 calories per gram, we find that the recommended range for her is 40 to 70 grams. She would aim to satisfy this amount by choosing different foods and beverages throughout the day. Starting from the right side, we can see that foods like non-starchy vegetables and fruit are poor sources of fat, as are starches like rice and pasta. Then, animal proteins like chicken, fish, and beef have a range of fat compositions. The amount differs within each one depending on the cut of beef or chicken or the type of fish selected. We can also see that eggs provide approximately 5 grams each, with the fat found in the yolk, and that plant-based foods like avocado and almonds are rich sources too. As we reach the left side, we find the foods that are highest in fat. That includes vegetable oils and butter, which contain over 10 grams per tablespoon. Our least desirable sources of fat are so-called junk foods like chips and donuts. Milk is an excellent example of a beverage containing various amounts of fat. Fat-free milk contains 0 grams per cup, whereas whole milk contains 8 grams per cup, with over half of it as saturated fat. Between those, we have options like 1% and 2%, which indicate the amount of fat in the milk by weight. As you can see, the more fat in the milk, the higher the calorie content. As mentioned previously, different cuts of beef contain various amounts of fat. The cuts that are mostly red in color, like fillet, rump, and flank, have a lower fat content than those with white marbling, like the ribeye, T-bone, and brisket. Variations of ground beef also reflect differences in fat content. That ranges from extra lean ground beef, which has a maximum fat content of 10%, all the way to regular ground beef, which has a maximum fat content of 30%. The next set of nutrition recommendations for fat is for saturated fat, which we have seen is the fat found in butter, animal protein, and milk. According to the DRI and the Dietary Guidelines for Americans, we should limit intake to a maximum of 10% of total calories. The American Heart Association has also published a recommendation. For adults with high blood cholesterol, bring that down to 5 to 6%. Unfortunately, saturated fat tends to be a nutrient that is overconsumed. In the United States, the average saturated fat intake is 11% of total calories, and only 23% of Americans consume the recommended amount. The Dietary Guidelines for Americans contains this infographic, which shows the top sources of saturated fat for the US population ages 1 and older. Sandwiches account for the largest proportion at 19%. That category includes breakfast sandwiches, cold-cut sandwiches, burritos and tacos, hot dogs, and hamburgers. The other top contributor is dessert foods, which includes cakes and pies, ice cream, cookies and brownies, and donuts and pastries. So, saturated fat is the common target for nutrition recommendations. Two other lipids that have received attention as food components that should be limited include trans fat and dietary cholesterol. However, in recent years, attention has shifted away from them. There's currently no recommendation made for trans fat in the dietary guidelines for Americans. That's because they're not a major issue after the FDA banned partially hydrogenated oils in 2018. There's also no recommendation made for dietary cholesterol in the dietary guidelines. The last time they contained a recommendation for dietary cholesterol was in the 2010 to 2015 version, where they recommended limiting to a maximum of 300 milligrams per day. That brings us to the question, why limit saturated fat? Recommendations to limit saturated fat exist because excessive saturated fat intake raises low-density lipoproteins, also known as LDL, in the blood. Those LDL are commonly referred to as bad cholesterol. LDL travels in the blood and delivers lipids to tissues. Some LDL is necessary to maintain normal tissue functioning, but a high LDL level increases the risk for cardiovascular disease by promoting plaque formation. As LDL increases, it damages blood vessels and triggers an inflammatory response. When this persists, the blood vessels narrow. Eventually, the flow of blood can be interrupted, resulting in a cardiovascular event like a heart attack or stroke. As indicated by its name, LDL is a lipoprotein, just like the chylomicrons we saw when we examined fat absorption. Other types include the very low-density lipoprotein and the high-density lipoprotein. These lipoproteins are made of the same cholesterol, phospholipids, triglycerides, and protein, but contain different amounts and have different functions. The primary function of chylomicrons and VLDL is to deliver triglycerides to cells. The primary function of LDL is to deliver cholesterol to cells. And the primary function of HDL is to scavenge excess cholesterol from circulation. Chylomicrons are formed in the small intestine, and the remainder of the lipoproteins pictured here are produced by the liver. While all the lipoproteins are necessary, the LDL and HDL are the ones that receive the most attention. So, we'll finish the lesson by quickly comparing them. As mentioned, LDL and HDL are made of the same materials but in different proportions. LDL have less protein and more cholesterol, phospholipids, and triglycerides. Furthermore, LDL and HDL have contrasting actions. LDL delivers cholesterol to cells, whereas HDL collects excess cholesterol and delivers it to the liver for excretion. Lastly, blood levels are associated with cardiovascular disease risk. We have already seen how a high LDL increases risk. Now we see that a low HDL also increases risk. Given the detriment of high LDL and the benefit of maintaining the appropriate amount of HDL, people often refer to them as bad and good cholesterol respectively. LDL, HDL, and total cholesterol can be measured in the blood, and each one has reference ranges to stratify cardiovascular disease risk. For example, an LDL of 160 or higher may be considered a risk factor for cardiovascular disease, while an LDL under 100 may be considered protective. Similarly, an HDL under 40 for males and 50 for females may be considered a risk factor for cardiovascular disease, while an HDL of 60 or higher may be considered protective for both sexes. With this, there are recommendations for lowering LDL and increasing HDL. Starting with tips for lowering LDL, there are 3 actions a person can take. First, they can identify sources of saturated fat in the diet and reduce intake. For instance, they could trim visible fat from beef or pork prior to cooking, or switch from whole milk to fat-free milk. Second, they can replace a source of saturated fat with an unsaturated fat, which does not have the same undesirable effect on LDL. An example here is to drizzle olive oil over vegetables instead of butter. The third action a person can take is to increase fiber intake. As we learned in Chapter 4, fiber binds to cholesterol in the digestive tract and increases the excretion of it. That forces the liver to pull from cholesterol in the blood. Unfortunately, there are no established dietary measures that can be taken to raise HDL, although weight loss can help if it's warranted and achievable. However, lifestyle factors that appear to affect HDL include exercise and smoking. People who need to increase HDL should be encouraged to engage in regular physical activity, and they should avoid or quit cigarette smoking and tobacco use. That completes the fourth and final learning objective. We discussed nutrition recommendations for fat. If you want to check out parts of the chapter that weren't covered, here are the sections I recommend.